In this video we do another power factor correction example, and anytime you're doing one of these types of problems it's always good to draw out the power triangle like I did right here. And then here's the problem. Okay, it's an exercise that's on Polylearn. We're told we have a motor with this power factor 0.85 lagging, connected to a source at 240 volts RMS, and there's a watt meter attached to the motor that displays 50 watts, and we want to know what the apparent power is. So we go back here. We know from the power factor being 0.85 that the angle of the power triangle would just be inverse cosine of that power factor, and that comes out to approximately 32 degrees, which, by the way, remember, this is not only theta but theta z, since they're equivalent. And then the fact that we're told there's a watt meter displaying 50 watts means that's P average. So you see that just comes from knowing the watts of these powers, right? Q has units of Rs, complex power, apparent power has units of volt amperes, and P average, the absorbed power by the impedance, has units of watts. So you see, now that we know the angle in one side here, we can find the others just from basic trig. So we know that tan theta is opposite over adjacent, so that's Q over P average. So Q would just be the 50 watts times tangent of 32 degrees, and this comes out to 31 bars. Alright, and then the hypotenuse is just going to be the square root of 50 squared plus 31 squared. And that equals 58.8 VAs. Alright, so that's the answer to part A. Alright, so it's just working the power triangle. Now, if we go back and look at the problem here, part B is, okay, well, what capacitor does it take to correct the power factor? And the frequency is 60 Hertz. So here, remember, the key thing is that, okay, so this is part B, correcting the power factor, so coming up with the capacitor value. So we want the power factor to equal 1, and we're going to do that by making the reactive power of the capacitor equal to the reactive power of the motor, the inductive part of the motor. So 31 VAs is what we have, and again, when we connect the capacitor to correct the power factor, right, here's a symbol for a motor that's often used. We connect that capacitor in parallel, and it doesn't matter what side of the motor you put that capacitor, either side's the same thing, it's in parallel. And we're told that this was an RMS of 240 volts, right? That's the source voltage in RMS. And let's see, the frequency is 60 Hertz, which is 2 pi 60 radians per second. Okay, RS for radians per second. So we want QC to equal 31 VARs. So to get that capacitor value, we know that QC is equal to VC squared over XC, right? So we can solve for XC. It's just going to be 240 squared over 31. So XC comes out to, let's see, I don't think I actually wrote down the XC, but we can calculate it real quick here. Bring up the calculator. We got 240 times 240, and then divided by 31. Oh, there we go. We'll round down to 1,858 ohms. Okay, and then the capacitor value is just going to be 1 over 1858 times 2 pi 60. And if you go ahead and work out those numbers, it comes out to a capacitor value of 1.43 microfarads. Okay, well that's going to wrap up power factor correction, and the last part of this course will involve concepts, definitions, and problems involving transformers.